Welcome everybody. I'm Zoltan Lehoczky, and with my colleague Almos Szabo, we will like to show you how we created a Posit implementation and actually a Unum type 1 implementation as well before that in a high-level programming language for the Microsoft .NET platform. And at the same time, we also created an FPGA implementation of that with our own .NET to FPGA converter called Hastlayer. So let's see. First, a bit of introduction about us. We are from a company called Lombiq Technologies. Day-to-day, we are doing .NET web development services, specifically with an open source content management system called Orchard. We are based in Budapest, Hungary, but actually all of our clients are from other countries, mostly from North America. And our customers also include companies like even Microsoft itself or institutes like the Smithsonian Institution. And when we are not doing web development, then we are doing some research and development like Hastlayer. In the first part of the talk, I will introduce Hastlayer in a bit of a detail, and then Almos will follow up with our Posit implementation details and how it comes together in the FPGA implementation with Hastlayer. So let's start. Just a word of warning before anything else. Hastlayer is pretty much in an alpha stage currently. It works fairly well, it has some nice results, but it's not production ready yet. Why this is the case and what we are doing to mitigate that, I will tell you a bit later. Similarly, our Posit work is pretty much ongoing as well. So, what is Hastlayer? Hastlayer, well, it's a tool that takes a computer program and creates some equivalent FPGA logic, so a piece of logic hardware. Probably most of you are familiar with FPGAs here, so I can also say that it's a high-level synthesis tool for software developers who don't want to know about FPGA details. By the way, who is not familiar with FPGAs here? Nobody. That's good, because then I will skip this slide and go further. What we are specifically targeting here is Microsoft's .NET platform, programs written for .NET. So what actually Hastlayer processes are the .NET assemblies, the common intermediate language assemblies. And that means that any .NET language can be used with Hastlayer. And that includes also C# and Visual Basic, but also functional languages like F#, or even managed C++, or even scripting languages like PHP, Python, and JavaScript. And by the way, since we are talking about .NET, it would be great to see slide 32 as well. .NET and C# itself and the C# compiler is, by the way, open source. It's cross-platform, community-driven. And although it doesn't have a supercomputing focus, it moves in a direction that it goes a bit lower level and higher performance. So in a nutshell, what we want to do with Hastlayer is to get the computing benefits of FPGAs for all software developers. That means that if your application or if your algorithm is highly parallelizable and is compute bound, the CPU bound, then we give you a tool to make it faster and consume less electrical power as well, since FPGAs are very power efficient, of course. Them being basically application-specific coprocessors in our computing model. And at the same time, it's just software development as usual, so nothing really new to learn. And now let's see a demo how you would work with Hastlayer. I hope it's not an issue that we will see a bit of a source code, specifically C# program code. So let's see. What we have here is an example of Hastlayer, which is, by the way, up on GitHub, so you can check it out in detail. It's called the parallel algorithm class. As the name also suggests, well, it's a massively parallelized Lehoczky algorithm. It's not something really useful or from real world, but rather is kind of an exaggerated example of the class of algorithms that are especially suited to be accelerated by Hastlayer and with FPGAs. And what we have here, there is a bit of boilerplate related to Hastlayer, but pretty much everything is standard C#. But what the algorithm does is that it takes an input number and then starts tasks. Tasks in .NET are basically an abstraction over threads. So when you start a task, then eventually the .NET Task Scheduler will select the thread from the .NET thread pool and execute that task. How many such tasks can run in parallel depends on the platform. On the machine where I recorded this video, it contains an Intel Core i7 processor with 4 physical cores and 8 logical cores. So the hardware level parallelism we'll get there is, well, around 8. But we are actually starting 280 tasks. 280 because that many will fit on our FPGA that we use for testing. Because these tasks, these 280 tasks on the CPU will, of course, still execute on those 8 cores or 8 logical cores. But when converted into an FPGA implementation with Hastlayer, we will have actually 280 copies of the algorithm. So on the FPGA, we will get a hardware level parallelism of 280. What's executed in these tasks is, well, pretty simple. There is a bit of conditional logic. Again, this is just an example, which is executed 10 million times, and then the result is returned back. Then we wait for all of these tasks to finish. And once that happens, we sum together the results of all of these tasks, which will be the result of the whole algorithm itself. And now we'll start this little console application. And what happens is that Hastlayer now creates the hardware implementation, which is basically VHDL source code, which is then fed to the specific vendor tool chain of the FPGA developer. And once that happens, then it will start to execute this algorithm on the FPGA 3 times. And finally, it will execute it once on the CPU. It happens, and we can see that on the FPGA it took around 300 milliseconds each time. Well, if you take a closer look, it actually took exactly the same amount of time down to the 10,000th millisecond, and the reason is, of course, that there is no operating system, no noisy neighbors, nothing else, just bare metal. But when we take the latency of the communication with the host VC into account, then we can see that it was just below 400 milliseconds. And the reason is that our little slow, cheap FPGA port uses a slow virtual serial communication channel, so there is a big latency. But still, on the CPU, it took around 3.6 seconds, so an order of magnitude more. Now, of course, this wasn't a very scientific measurement. My machine was doing a lot of other things. But even without that, it would be below 2 seconds still. The point is, you can get a substantial performance increase by using FPGAs if your application is like that. And while this is the state of Hastlayer, we are working on supporting bigger, faster cloud FPGAs to make it actually production ready. And now my colleague Almos will take over with our Posit work and how it relates to Hastlayer.
So we started out with Posits because Hastlayer needed some kind of floating point support. And we heard about Unum Type 1 first, and then also Posits, and how they aim to make computations faster and more energy efficient. So those are the same goals of Hastlayer. So we thought that they would be a natural fit for us to use. So we have made our implementations in .NET C#. All of our implementations are open source, and we have also transformed our code to FPGA logic using Hastlayer. I would like to give you a quick overview of our implementations, since there are 3 of them. So first we implemented Unum Type 1s, and that is a universal implementation, and then we also implemented made a universal Posit implementation, and we call them universal because these implementations are capable of handling any environment, so any size of Unums and Posits you can use with them. And then we have also made a fixed size Posit implementation. So we started out with Type 1 Unums. Our implementation is capable of handling any size of environments. We got to a proof of concept level with Type 1 Unums. We got addition and subtraction working. And to be able to support any size of environment, and also because Type 1 Unums are variable size by nature, we needed an underlying structure to support that, so we came up with bitmasks. Bitmask is an abstraction. It's basically like an arbitrarily sized unsigned integer. So it can be any size you want, and it contains the bits of the Posits and Unums, and it is capable of the low-level operations that any number format might need, such as count leading zeros, addition, and bit shifting, and so on. Unfortunately, to do that on a CPU, it needs to use an array and for loops and some carry logic, so it's slower than we'd like it to be. Then by the time we got to this point, our type of Unum implementation, we heard about Posit. So we switched to... Okay, this one works, thanks. So we switched to Posits instead because we like the fixed length, especially on FPGA, and we also like the idea that they could be drop-in replacements to IEEE float. So our universal Posit implementation also handles any size of Posit environment. It also needs to use bitmaps to do that, and so it's also slower than we'd like it to be. Basically, that's why we started out with our fixed size 32-bit version, which is based on built-in .NET type, namely unsigned integers. And we got a little further with that, so it got addition, subtraction, and multiplication working. And it uses significantly less resources and is much faster because of ditching the bit masks. So here is how much resources each of our implementations used up on our Nexus 4 DDR FPGA board. It's a small development board. So as you can see, the type 1 Unums, well, all of the examples are considering additions, because that's what we have. So the type 1 Unums use the most resources, and our universal Posit implementations were somewhat more hardware friendly than that. And of course, because of replacing the bitmaps, our fixed size Posit additions were the most hardware friendly of them all. So we have made some performance measurements. Our benchmark test was performing 100,000 additions, both on the CPU and on the FPGA. We used the first generation Intel i7 CPU with 3.2 gigahertz and the small development FPGA board with 100 megahertz. So that is important to think about when we compare these results. And the additions weren't parallelized yet here. So, and as you can see, the universal Posits were really slow. It took more than 2 seconds on the CPU and more than 9 seconds on FPGA. So that's why we switched to 32-bit Posits, and they perform much better. So with the CPU, with the 32-bit Posits, we have reached about 7.7 million Posit operations per second on this order CPU, and about 500,000 Posit operations on FPGA. You also have to note that this is managed code, so when you compare it to, for example, a native C++ implementation, keep that in mind. So the interesting thing is when we compare the clock cycle efficiency of the two devices, because the FPGA was over 7 times more efficient per clock cycle compared to the CPU, and over 2 times more efficient with the 32-bit Posits. So we think that this is roughly proportional to the power consumption efficiency of these devices also. So we also made a parallelized performance test. As you can see, with the 32-bit Posits, we have made 500,000 additions in parallel on 5 threads, so 100,000 additions on each thread. And on the FPGA, it took exactly the same time as adding 100,000 Posits in only 1 thread. So it is really scalable in parallelization. While the CPU ran out of physical cores, because we use 5 threads, and it has only 4 physical cores, so the CPU took almost twice the time to perform the 500,000 addition like it. And when parallelized with the CPU, we could reach about 23.8 million Posit operations per second. The FPGA, almost 2.5 million Posit operations per second. So, of course, with parallelization, the clock cycle efficiency of both devices has increased. But while the FPGAs has increased linearly, so it became exactly 5 times efficient per clock cycle, the CPU got only somewhat more efficient. So now the FPGA implementation is over 4 times more, almost 4 times more efficient per clock cycle than the CPU implementation. So what we are planning to do next, we will implement all of the operations to make a fully functional Posit library and to be used in any kind of .NET application. We will also implement acquires for that to be fully Posit compliant because well, this is ongoing work now. And we will also make 8, 16, and 64-bit versions with code generation. And we are also planning to implement valid arithmetics. So now I will show a little demo too, just to showcase how easy it is to use our Posit implementation in any .NET application. So this little method, calculate integer sum up to number, is the one that we are going to run both on the CPU and on the FPGA board. What happens here is that we read a number from the memory. In this case, it is going to be 100,000. And then we create a new Posit out of it. So it's really easy, just like with any other struct. We give it the integer value of 1. Then we copy it into the variable b. And then we, in a for loop that runs 100,000 times, we add this Posit b to the Posit e. So we'll hopefully get 100,000. Basically, we just count up to 100,000 here. And then we cast our result back from a Posit to an integer with a simple cast. And we write our result back into a result variable, and then write this result back into the memory. So it's just to show how simple it is. But it also works with floats, of course, not just integers. We got the floating point conversion working too. So let's see how it works. We already got the software result. It's the uppermost line. It took 122 milliseconds on the CPU. Well, because it is in debug mode, so you can come and see our demo back where it will be in release mode. And so now we are waiting for Hastlayer to generate the equivalent hardware logic, the VHDL files. And once it happens, we will see how it runs on the FPGA. It only takes a few seconds, so that's how fast it is. And yeah, well, down there we see that on the FPGA board it took 211 milliseconds without the communication round trip, and 290 milliseconds altogether to perform these additions. So that's really just to show how these things work. And thank you for your attention. You can find more information on the links above. All of our code is open source. You can find it on GitHub. And please come check out our code at our demo table in the back of the room. Thanks.
All right, we have time for questions.
Yes?
What do you know on the CPU, right? How
Yes.
many cycles and number of operations?
It's an estimate. We calculated it backwards from the time it took and from the
Basically, we have taken the clock speed of the CPU and the time measurement it took to execute the whole sample. The CPU was actually running at 3.2 gigahertz, so it wasn't scaled down.
If you run the perf, you see a lot of things.
Yeah.
So it's very confusing.
Yeah, it's surely not an exactly. I have a mic. It's surely not an exactly accurate measurement for the CPU part, but as mentioned, the CPU was kept out at 100%, so we can reasonably estimate that it was consuming most of its clock cycles.
I have one question. So, page 18.
Okay.
So what's exactly on the y-axis here?
The y-axis is how many persons of the FPGA board was actually used by these implementations.
And by resource, you mean?
Well, it's detailed in our paper. We mean the most used resource of the board here. So the one that was.
So the DSPs or the LUTs? Or
Well, it varies from implementation to implementation. Mostly the flip-flops, I think, but not in all of the cases. But you can find it in our paper, which is going to be published online. There is everything very detailed. It is just because of the shortage of time.
Please.
Does the Hastlayer support another kind of FPGA, such as FPGA with more resource? Is it possible?
Not yet. So the only FPGA we support currently is that small development board that we also have here on the demo table, which was easy to begin with, but and easy to work with, but of course only usable for testing. We are working, however, on supporting bigger FPGAs. Actually, that of the Microsoft Catapult FPGA Cloud, which will possibly eventually be the Microsoft Azure FPGA Cloud. Yeah, those are, well, it's hard to compare, but probably 50 times more powerful FPGAs than the one we have here.
How much is this board that you're using?
You mean in money? Yeah, it's around $300.
If not, let's thank the speakers again. Thank you.
Right. Thank you.
Thank you.
And